Okay, so let's go to the core of this course, high-level synthesis. Okay, high-level synthesis basically convert high-level description written in C, C++, or OpenCL. And for Xilinx, it is a C and C, C++. And Xilinx, I remember in newer version they drop before they support System C, and then they don't no longer support System C. Yeah, and Intel support OpenCL. Okay, that's Intel. Yeah, that's Xilinx. Okay, so its output is the RTL circuit. So it's a RTL code or VHDL. Okay, VHDL or Verilog. So you can based on user feedback to optimize for power, performance areas. And for the designer, you use either directive or pragma. Yeah, we just introduced directive and pragma. Yeah, in the lab too. Yeah, and user control the compiler process through these two means, either directive and pragma, and they are twins. Yeah, they have a one-to-one mapping of those two. Yeah. Okay. And for right now, the HLS vendor, mainly from the FPGA vendor, and many from the Xilinx or Intel. And from the IC vendor, you see the Siemens Mental, Cuttable, or Cadence Stratus. And for Synopsys Symphony, they seem quite slow in their development, so I don't see much exposure from Synopsys. Yeah, and to tell the truth, the best HLS compiler is from the Xilinx. Yeah. And in a meeting with Mental, they introduced Cuttable that. I asked them that how do you compare your Cuttable with Xilinx Vivado HLS? Their answer is for some cases their Cuttable result is about the same quality as the Xilinx. So from his answer, I think he's quite frank that the mental graphic Cuttable that the result is not as good as Xilinx. And I believe for the IC vendor, mental Cuttable probably has the best, yeah, compared to Cadence. Yeah. Okay. So this give a flow. So basically, you have a high-level code. You do a syntactic analysis. Basically, convert the high-level code into an intermediate presentation. Okay. And from that on, that's the HLS. That's the HLS compiler. Yeah. And in this optimization, that's basically perform compiler-like optimizations. And the real core of HLS compiler is in its backend. So it's optimized, especially good for data path type of descriptions. Yeah. Basically, it's a arithmetic description of the your algorithm. Yeah. So it's strong at the doing the scheduling. The function include the scheduling the resource allocation and the binding the resource and resource sharing. Yeah. So when we talk about HLS, most people direct impression is it's good for the data path. Yeah, so that's the data path compiler. Yeah, and the data path compiler, the major function is doing the scheduling, resource allocation, binding, and resource sharing. And then we will see in the later example how is it done. Okay, first I would briefly on what C construct that is not supported by the HLS. And I will go through a C to RT mapping flow. Yeah. And then I will show two examples in greater detail on how the HLS process. Basically, that's very much like our design process. I tell step by step how to do an expression, a typical data path design, and the control flow. That's a for loop. The following construct in C is not supported in HLS. Okay, first is the system call and the dynamic memory usage, like mlog, alloc. And there's no C++ dynamic polymorphism, and there's no dynamic virtual function call. And there are a lot of restrictions on the pointer usage. We know C++ uses a lot of pointers, but they have a very limited use for pointer. Yeah, and it does not support recursive function except for the case the tail recursion that I will introduce later. So basically, the basic rule of thumb is all resource must be statically allocated at the compiler stage. Yeah, if your code, for example, like a recursive function that cannot be supported because the level of function code is really data dependent, and the data is a runtime data. Yeah, so in that case, if it cannot be statically allocated compiler stage, then it cannot be supported by HLS. So that's a rule of thumb. Yeah. Okay, let's look at the system code. Yeah. System code is quite important in developing our applications. For example, we will dump some intermediate result to a file to either doing the debugging or diagnosis. It's very handy to use the system code. For example, like time, we want to measure the runtime. Yeah. So so we like the whole application could be run with the system code. However, certain portion of the application code has to move to HLS, but HLS doesn't support the system code. So that's why in HLS it defines a macro synthesis underscore synthesis. This macro is defined in HLS. Okay, so we can use this to separate the part with synthesis and not synthesis system code in one source code. Yeah. For example, in this hierarchy function, it is a kernel function. Yeah. And when you do the C simulation, integrate with this kernel function. In the C simulation, this synthesis is not defined because this is only defined in HLS compiler. So when you run the C simulation, you have all the debugging capability at hand. So you have a flexibility to all kind of normal C function for debugging. And when the same piece of code going through the HLS, and this is defined, so this part of code will be ignored. Yeah, so it still function in the HLS compilation. Yeah, so it's a good coding style. Yeah, using the undergo synthesis. Yeah. Another is dynamic memory usage. Okay, again, that's the same piece of the kernel function that you want to run in C simulation, and the same piece of code you want to run in HLS, but HLS doesn't support man allocate. Yeah, so you can define. Okay, this one is user defined. It's not available in HLS. You have to define it by yourself. Okay, So when doing the C simulation, then you have to define this macro. And when you want to run this code in HLS, then you comment it out. Okay. So you know the mallocate and this one in the in the HLS, all the memory or the data has to be statically allocate. So you have to allocate this memory, and then you have a pointer point to that, and then you have to physically allocate the size of memory, yeah, and have the pointer, this pointer point to the point to the array, yeah. And in C simulation, that mallocate that actually introduce the OS function. Yeah, often that why we want to use the mallocate? Okay, because the mallocate is an OS function. Suppose you want to develop a kernel function that can process a big data, and the data amount of data simply could not fit into the system memory. The amount of data may be have to store in the hard disk. Okay, so for sure, you could not allocate that much memory statically in FPGA. Right. So for doing the C simulation, you want to be able to handle the bigger amount of data, so you have to use the allocate. Of course, you can write the same code in doing the C simulation. Yeah, but as I said, if you want to process that big amount of data, simply could not fit into the FPGA, you have to use the allocate. So that's the situation that you use the node synthesis. So doing the C simulation, you use the allocate, then you can process bigger amount of data. And in actually HLS synthesis, this could be only a cache or something, maybe a small amount memory, but to process the external big memory, you may have another module outside to pre-process and feed into here. Yeah. So I don't know whether you can understand what I'm saying. Yeah. So basically, yeah, remember, yeah, that high-level sensor could not use the MLK. Yeah, that's all you need to know. Okay, pointer limitation. First, it could not support general pointer casting. Okay, but it can pointer casting can happen between native C++ data type. What is the native data type? Like a byte, short, integer, or float or double. Okay, those are the native C++. Then you can do the pointer casting. Yeah, it supports that. And pointer array, yeah, it limited to support only pointer array to a scalar or an array of a scalar. Yeah. It could not support array of pointer and point to additional pointers. Yeah, actually, for the coding flexibilities, people use a lot for this kind of data structures. Yeah, but unfortunately, it doesn't support in the HLS. And function pointer definitely, yeah, not supported. So for HLS, it has only limited pointer usage. Yeah. Okay, recursive function. It doesn't support recursive function. Yeah. It could not be synthesized simply because the function code depth is data dependent. Yeah. So it's a non-determined at the compiler type, so it cannot support. However, tail recursion it can support, only support in C++. In C, it could not support tail recursion. Why tail recursion can be supported? Because tail recursion is a loop, actually it's a loop in disguise. For example, in the GCD example, and this is a tail recursion. So this code can be easily transferred into this one, non-recursive version. It's a loop. Okay. So if you want to use a C++ to support tail recursion, then the key is you need to define a termination class. So for the Fidelity, there's a recursive function, yeah, can be written with a terminal condition, which is this one is a termination conditions. Yeah, if we write the recursion in this way, then the HLS can support this kind of tail recursion. Yeah. Okay. Oh, okay. So let's go to C to RTL mapping here. Okay, in here, that's a typical FIR code written in C. Okay, let's investigate the syntax in the C language. First, you have a function call, function name. So the function name, it will map to the module, the Verilog module. And you have an argument, okay? The argument, those are argument with the data type, okay? So for argument that map to the module I/O interface port, that's quite intuitive. Yeah. And you have a type. Why we want to use C, C++ for high-level sensor instead of Python? One of the reasons is C, C++ is a strong type. For every variable, you have to explicitly specify its data type. Yeah. And with the explicit data type, then you have known the resource at the compile time. But for Python or other Java, those high-level language is so high level, so it doesn't have a specific data type until it happens at the runtime. Yeah. So in that case, that's HLS has a great difficulty in dealing with that. You cannot allocate the resource, hardware resource. Okay. And all variable must have a defined data type, and the data type is influence the area and the performance a lot. So we will have a special separate chapter talking about the type. Yeah. And the argument we will talk about in the I/O interface in greater detail. And the type, we have a chapter data type to talk in greater detail. Yeah. And in the main body, it has a loop. Okay, the loop is the main focus in HLS because it impacts on the area and performance. Okay, and we use the directive pragma to control the level of parallelism. Yeah. And we will have a chapter pipeline and data flow dedicated to explain the loop. Yeah. And we have like this control flow, control logic. Yeah. And we use a lot of array. Okay. And array actually translate into the memory. Okay, it also impact the device memory and performance because for performance, a lot of time that depend on the data bandwidth. The data bandwidth are limited by the memory port. Okay, And we have a dedicated chapter talking about memory in the memory chapters. And also, that's an expression operator. Okay, and that's where the data path comes in. Yeah. Okay, in the following slides, I will explain each of these constructs from the C code. Okay, first, function hierarchy. Okay, functional hierarchy, the top function for every HLS synthesis, you have to specify top function. Okay, the top function becomes the top level of the RTL. Yeah. And then sub function becomes the RTL called sub blocks. Yeah. For example, in this example, okay, you have a top function, you call function A and B. Okay. And the B function, you call the function C. So when it generates the RTL code, you will see you have a top module, and you have a module A and module B, and also C. So you will see separate variable code. You have a top.v, you have A.v, you have B.v, and C.v. And there will be a range in the hierarchy structure, simply like your C code function code hierarchy. And you can inline to dissolve the hierarchy. Okay, for this function you can call inline. For example, you inline this C function. The C function will be dissolved to the upper layer to B. Okay, this is a function hierarchy. And you have a function argument. Okay, the function argument will map to the port on the RTL block. So the function argument is used to transfer data in and out of the kernel function. Okay, that's a function argument. Yeah. So for example, for this function, you have A, B, C inputs, and you have a output return. Okay. And then so you will create A, B, C data port and the return port. Okay. In additional, you have other control signal. Additional control port are generated for this design. The purpose is to control and synchronize among blocks. For example, this return may go to the next module, right? So for next module, how this module knows the return is valid? So you need this signal, the result valid signal goes out. So this module, when it sample the valid, then it shows the return data. Yeah. So the function argument, it has two parts. One is the data port, and one is the control interface protocol used. Yeah. And this, what kind of protocol you use? You use a pragma. And you can specify the interface, what kind of protocol you want to use. And every type of argument has its default interface protocol. You can simply use a default one, or you can specify your own. Yeah. Okay. So the function argument is how you connect to the communicate with the host. Okay. For example, in this example, okay, you have a in one, in two, and in out. Okay, simply add them together. The function is simple. Yeah, and then you use a directive. You specify the function block is control handshake. Okay, For this, you may not understand this moment, but you just get some idea. Yeah, and because you will be introduced in the I/O interface sections. Yeah, and then in one is using the handshake protocol. In two using the FIFO. Okay, so when you specify the interface type, it will generate different control signal. For this part is a block level handshake. We all see that AP star, AP down. Okay. And then for in one is a handshake, so it generates additional control signal, valley and egg. And in two we said that's a FIFO. Okay, it's an input, so it generates the protocol is AP FIFO. So for AP FIFO, in addition to the data, it generates additional two control signal, the empty and the read. And the in-out is a bidirectional signal. It's an input and output. So it will separate into the input part and the output part. And that's it says it's a bus interface. Yeah, so it generates the corresponding control signal. And remember, to communicate with the PSI, it has only XI master interface, right? Yeah. So those protocol signal going through adapter. Okay. The adapter is when you're doing the IP generation. Okay. So when you're going through the HLS compiler, this module will generate all those interface signal. And this signal is far from this XI master. Okay, so when you do the IP generation, you will hook up some adapter. And then it becomes the XI light, XI slave, XI string, or XI master. That's how you see in the lab 2. You see that icon, the kernel function icon, only have this kind of interface available. Okay, and then through the block design, hook up some other interconnect, like the interconnect, like the stream to memory or memory to stream DMA. That's I call infrastructure component. So infrastructure component includes the DMA, include the fabric. Interconnect is the fabric. Okay, and for the software, in order to hook on the OS and API, it has a metadata and the driver. That's the infrastructure. So by impose those additional components, then you can communicate with the host. Okay, so now you have a step of a process. Yeah, from the kernel function to how you can communicate with the host. Okay. So that's the argument. So when doing the HLS design, the argument, function argument is a very critical part. And that related to the chapter I/O interface. Yeah. So I will explain in greater detail in later chapter. Okay, for expression. Okay, so this expression is something like that. Yeah. So for the expression, eventually this expression will be translated into data path part and the control part. This expression eventually will generate this kind of a logic. Okay, so the first step is put this into a data flow graph that shows all the data dependency. So you draw this data flow graph. And next step, you will do the resource allocation. That means for each operator, you will specify what the hardware resource you will be using. For example, you need a multiplier, you need the adder. And at this stage, the user can specify how much resource you want to allocate. For example, in this example, designer says for this adder operation, okay, for this adder operation, I only limited one adder. Okay, in here, this expression, you have two adder. So since you allow only one adder to use, so this thing could not be complete in one cycle. Because if you want to do everything in one cycle, then you need two adder. Right, so you need at least two cycles. Yeah. So you do the resource allocation, and then you do the scheduling. Okay, scheduling means which cycle and doing what operation. Okay, so for this one, he doing the schedule, say the first cycle, I want to do the multiplication between A and X, and then add B in first cycle. And the result will add with C in the second cycle. Okay, so that's then we decide the scheduling here. Okay, and then we want to do the binding. Binding means you assign to actual physical resource. Okay, so initial binding for multiplication, I decide using the CLB combinational multiplication, and then using an adder, I use this adder. Okay, and the final target binding phase, I decide. Oh, this actually is a MAC. Okay, so for FPGA, it has a DSP block. And DSP block, you can do multiplication and add in one DSP. So they decide, combine, I want to use a physical DSP 48. And the second one, I bind to actually an S sub. Yeah. So this complete the data path design. Yeah. Okay. So now you know the steps. Okay, first you have to draw the DFG data flow graph, and then you based on your resource allocation. In here, I decide using only one adder. Okay, in this case, then I do the scheduling, assign the operation in different cycle. Okay, and then I binding the actual hardware. Yeah. So that's the so-called data path compiler. And it's basically it's the core of a high-level synthesis. So high-level synthesis is really good handle this data path compiler. Okay, array. Okay, so in your SQL you use a lot of array, and it typically implement using the memory block. Okay, and if it's a constant array, you map it to the ROM. Okay, and array when you do the parallelism, array often is a bottleneck because array map to RAM, right? And RAM has one or two port only. Yeah, if you have too many parallelism and people or the design want to access the array at the same time, then you're limited by the memory port. So the HLS provide several mechanism to relieve this memory bottleneck. So the same array you can partition into multiple RAM. Okay, when you given an array, you partition into multiple RAM. That means you increase its bandwidth. Yeah, because it provides more memory pool for you. And or the array, multiple array, you can merge and map to single RAM, because in your C code you may have many small arrays, maybe only 10 bytes, but for FPGA, each memory block is 18 K bits. Yeah, so you better efficient use your FPGA memory resource. So you may want to have a multiple array merge into one RAM. And often in the case that we want to map array partition into the registers. For example, when we are doing the convolution, so you have the convolution kernel function, for example, 3 by 3, and you maybe declare is a 3 by 3 array. Okay, that's an array, and by default you will becomes a memory. And we want to do this 3 by 3 kernel function in parallel, right? We want to do this 9 operation at the same time. So in this case, you can partition into individual registers so that you can parallel operate on the every element of this kernel function. Yeah. So those things, HLS provide all the mechanism that you to manipulate the array without changing your C code. Because when you change the array configuration, if you encode the RTL code, it's very easy prone, error prone, very easy to make a mistake. And control flow, okay, many we talk about loop, and that's for parallelism mostly come from the loop. Yeah, that's the main focus for HLS. Yeah, and to make a loop parallel, that you basically have a few problems. One is data dependency. One is the memory bandwidth. So that's often when you try to parallelize a loop, that's the two typical difficulties that you have to face. Okay, loop are the main area of parallelism. Okay, and loop can be pipeline, enroll or partial enroll or merge or flatten. Yeah, and here I give you a very brief high-level idea what it's talking about. For example, row. Okay, so for the loop, by default is row. Okay, so loop is row. So each loop iteration is a corresponding sequence of states, and so the state. Okay, for example, like this loop is a state. The state just iterate until for the trip count. Trip count, for example, for the for loop, the loop limiting vector, limiting number like that's 3, that's trip count. So the same loop will repeat that many times. And the operation resource is repeatedly used. Okay, so you can very efficient use the resource longer latency. So let's take this a very simple example. So if it's a loop, so it generates a code like this one. First, you try to load the array. There's a load AI, and then you doing the add with B, and then you continue loop. And so this state 1 and this state 2. Okay, so you continue the loop. So you use the same adder repeatedly in different iterations. Also. So that's row 1. Yeah. And you can enroll. Okay. When you use a pragma enroll, if you don't specify factor number, that means you want fully enroll. Fully enroll. Okay. For example, like this code, the loop will loop 4 times. Okay. So if we use the enroll, if you enroll, that means the same equation repeat. Yeah. Okay. So in here, if you want to do this all at the same time, you will see you need 4 multiplier. Okay. And you also need 4 read on A and 4 read for B and 4 write for C. Okay. As I said, in the FPGA, each memory has a maximum 2 port. So in this case, you simply could not fully enroll it, right? So if you don't want to waste the memory resource, the maximum you can do is enroll with a factor equal 2. Then you can use a 1 block run to store A array, B, another block run for B, and another for C. Okay, so factor 2. So if you insist, I just want to do a fully enroll to get the maximum performance. In that case, how can you do? Then you need to have a memory partition. That means the A array need 2 memory block, so that each can provide 2 A array content. Each provide 2 A content. Okay, so if we use enroll 2 and you use a memory array partition, you pass an array partition. Okay, the HLS code will generate this kind of a circuit logic for you, and then it generates all the address generation, and all the control for you. So you don't need to worry the detail how the logic is designed. You simply use this pragma. Yeah. And then the HLS generate all the necessary control logic for you and data path. Okay. So I strongly I saw from the review of students' projects, I saw people want to manually enroll it, like this one. Okay, instead of you use pragma enroll, you can simply write the enroll. He actually write the code like this one. Yeah. So once you write the code this one, then you cannot make a factor equal 2 with the same host code, same source code. Yeah. And if you use a pragma, you just change factor. You can say factor equal n, and the n defined in the header file. Okay, and then you change n, for example, equal 2 or equal 4, then you generate all different parallelism of the same design and using the same source code. So try to avoid to restructure your code, which that pragma can do that for you. Yeah. So try to avoid writing code like that one. Yeah. Unless that's something that's so niche or so corner cases that the pragma could not do it for you. Yeah. But basically try to avoid it. Enroll. And then loop can be pipeline. Yeah. And pipeline is one of the most important optimization. Why? Because the pipeline is quite efficient. Okay, you can think that enroll is like a brute force. You duplicate hardware. Okay, if you want to get twice of the throughput, that you double your resource. For pipeline, actually the resource use will be very efficient. So we will use pipeline, loop pipeline a lot instead of using enroll. Yeah. So it allows a new iteration to begin before the previous iteration is complete. Yeah. For example, for this operation, it take a full cycle. It take a full cycle. So if you want to do the no pipeline, okay, your throughput will be 1/4, full cycle and generate one output, right? And then if I use a pipeline II equal 1, then you can generate for every one cycle you can generate one output. So you actually 4 times your throughput. Yeah, and your resource use will be much limited. Yeah. So for pipeline, there's a key matrix, which is the initial interval. Initial interval means how many cycles that you can take a next input. For in this case, II equal 1. So that means one cycle later, you can feed another input. Okay. So when you're doing the pipeline, that within one cycle, you have overlap iterations. That means you need to have enough resource to support those pipeline. In here, if you look at this cycle, you will find out you have a load. The load here actually load A array and B array. So you have a 2 load and 1 store here. And also you need to do two multiplication here. So for the multiplication, you have a 2 multiplication multiplier, or you use the pipeline multiplier. Okay. So for pipeline, we talk about that one is the memory bandwidth, and also you need to have enough resource to do that. Yeah. Okay. So in here, I'd like to demonstrate an HLS process. Yeah. Okay. Let's first take expression. For doing the expression data path, the resource allocation and schedule. Let's see. So that's the expression you have. So from the expression, you can draw a data flow graph, DFG graph. You draw like this one. Okay. So you see A plus B generate a B output, and B plus B times C generate W. And V plus C generate X, okay, and so on. So you draw this graph, okay, and then you decide the resource allocation. Either the designer specify how much resource he can use, or the tool decided for you. Okay, in this case, the user specify I just use the 1 Mac. Okay, only one hardware can do either one multiplication or one adder. Okay, with this resource allocation, you decide I want to do the scheduling like this one. Okay, so that means the first cycle I can do the add, and second cycle and the third cycle I do, because the multiplier is a 2 cycle operator, take 2 cycles. Okay, and then I put this in the fourth cycle and fifth cycle and this sixth cycle. So it takes 6 cycles to complete this expression. Or the designer says, oh, I can allocate one adder and one multiplier. So that means you can do 2 operations in the same cycle. So in this case, then the tool will figure out the scheduling like this one. So first cycle, you can do the add and multiplication. Okay, and then here another. So you can see for every cycle, you use one adder and one multiplication. Okay, so right now I have a scheduling here. Okay, and then I take the scheduling result and go to the next step. So given this scheduling result, then for each clock, then I can design a state. The state is quite simple. From the idle state, in the idle state, you are given A, B, C, 3 arguments. And then for each cycle is state 1, state 2, state 3, and state 4. Okay, and then right now I'm starting designing the data path. And as you can see, you can only have a 1 adder and 1 multiplication. Okay, so for each adder, that and actually you will need to decide the state variable. Okay, state variable become your register, and that's your operator. And for each the state variable, you have a multiple input, so you have a max select. From each, for different cycle, you will select different source. And for the adder, you have a 2 operand. For each operand, you have a different resource coming from. And multiplication, you have 2 operand. The same thing, you could from different state variables. Yeah. Okay. So you roughly sketch the data path. Right now, the problem: how do you decide the max select and the register latch control? You need to decide all those control signal. Okay. What I'm talking about when as a human to design the RTL code, we are doing the same thing, but we just doing manually. Yeah, the design process as you design RTL code is exactly the same. Yeah, and then you will try to draw this table. Okay, first you figure out 2 operator, and then you have how many state variables. So the question here, you have a 3 state variable. Is that enough? The state variable is a register. If you look at this schedule DFT, so for every clock age, how many data will pass through this age? You can see here, this cycle here, you have an ABC. So at least you want to save an ABC. And on this clock, on this cycle, you have a 2 pass. And for this cycle, you have a 1, 2, 3 age crossing the clock cycle. And here you have a 2. So you know you just need maximum 3 state variable. But at a different clock age, you have a different source fitted into these state registers. So that's why you have a max comes in. And for the adder and multiplication, the operand coming from different from the 3 state registers. But different cycle, you choose different source of the operand. Okay, so based on that, you can draw a table. So basically, you want to have control the 3-state register. You have an adder, yeah, and that's for state register. You have a source control, the multiplex where the source coming from, and you have a whether this register will be enabled. Okay, for the adder, you have a select 5, select 6. You have a 2 operand select, and multiplier, you have a 2 operand select. And then you look at each cycle, you can draw a table like this one. Okay, so that's for state 1, state 2, state 3, state 4, mapping here. So from that, you can code, draw this table. And right now, I want to generate the select. For example, I want to generate enable 1. This is a register enable. And you look at this table. Enable 1, when does enable 1 active? You can look at here, that at the state 1, state 3, and state 4. So there's state 1, state 3, and state 4. So you generate the control signal. Okay, so at the end, you will find out this is the data path. Okay, those component are data path. And all those control signals, select, enable, is generated by the finite state machine. There's a control logic. So the control logic here record the state machine and also generate the output control signal to control all the data path flow. Yeah. So this complete the expression synthesis. Yeah. Eventually, so high-level sensor basically generate data path and it's a corresponding control signal. Okay, so this one example. Another example, I like to take a control flow. Control flow like the for loop. Right now, I want to design a logic to do this loop. Okay, first for this loop, it generate a DFG. Yeah, composed into the state. Yeah. So you have a first state here, initialize the accumulator initialize to 0. Okay, and then you want to have the loop index I initialize to 0. And then you next check whether I less than the index bound. Right now it should be n. Okay. And then inside the loop, you want low A array. And then you want to add, and then increment I, the index, and then coming back. If the index I reach is a limit, then it's done. Okay, so then based on this, the compiler techniques is easy. You can generate the flow control graph. And in the flow control graph, and you want to identify the state variables. In this example, state variable, you can think that's a register. I need to identify certain register that you need to keep those values across clock cycles. So in here, what state variable you need to keep or operand you need to keep. One is the loop index variable and the accumulator, which is declared here, right? I and yeah. And then when you load the AI array, you need to save it. Okay. And then you the AI is an array, then you need to generate address to access the external memory array. So you need to register state variable like this one. And then you can draw for index I, you will add 1, and then you will do the comparison. Okay, for accumulator, you need the adder. And for address, because each time the I will increment, so the address will increment 1 each time for each loop. So you define the state registers, and then for each state register, you decide the source and state variable input. It's just like the previous expression synthesis, very similar. So you have decide each of the state register the source. So you have a mux, and you have an operator, a state registers. So doing the same thing like the previous one, then you can generate all those control, the mux select, the operator source select. Okay, here. So then you design the controller, the synthesis, the controller generate all the control signal. Yeah. And the control signal, the state machine generate the dump and the memory read command, and the data path will provide the memory address and the final accumulator result. Okay. So after you have this idea, okay, and then let's take this code. You're going through the Vivado HLS. You try to investigate the interface. Okay, first for this part, that's a block level protocol, and you have a return because you return the ACC. Yeah, so you have a output return, and since you need to access the array. So for array, you generate the address, the memory access address. You have a chip enable and the data output, the memory array output. Okay, so that's the interface. And then you can investigate the scheduling. Yeah. For the scheduling, you will see like this is the I. Okay, and you can see the I is being used for doing the comparator. This one is the comparator. And this one is add 1. Okay, and I also goes here. Okay, what's this operation? That's a read a load A array. So I becomes the address of this memory array, access the memory array. Okay, the memory array output will add I didn't click to show another one. Yeah, you can add together accumulator add here. Okay, so I will recommend you carefully study the scheduling waveform here. When you have a piece of a code after doing the synthesis, do investigate the schedule waveform. And in the tool, when you click one, it will show the source code. So the tool is quite friendly compared to before the previous version I used 2019.2. It doesn't link to the source code. But in the 2020.2, the tool version you are using, when you click one, it will link to your source code. Yeah. So you can carefully study the data dependency here and your source code. And especially when you find out the loop take, for example, it takes 2 cycles for the loop latency. It should be iteration latency. and you find out it takes too long, then you can look at this to find out the bottleneck. You will find out, oh, which will create actual cycles. Is there a way I can reduce it? Or due to the data dependency, that it cannot, it has actual cycles. Yeah, so study this. And then you can look at the resource. Okay, in here, you will find out the resource is a little bit different from the previous one. In the previous, we see we need have a 3 adder and 1 comparator, right? Yeah, but the high-level census only use 2 adder and 1 comparator. So there's 1 adder missing or not used. And from this, we see for the address translation, address generation, it use I directly. Okay, it doesn't. But however, to generate to access this array element, of course you need I. You also need A, right? You need A plus I. Yeah. To access. But this A, it seems it doesn't have a adder for this one. Yeah. So it's come back to the this one is actually not in the HLS kernel. It's in the adapter circuit. It's a little bit complicated because the A is in the AXI Lite. It's not part of kernel. This is your kernel function. Remember, you have a adapter module. Yeah. And the adder, this adder A plus I. For the kernel function, it only supply I here. To generate the array access A plus I, A plus I is outside. Yeah, so it doesn't come into here. Yes, yeah. So end up, yeah. So that's the example to do the control flow. So I don't know whether how much you can get this. Yeah, I would suggest you really study the scheduling waveform and investigate with corresponding source code to do the cost reference. Then you will have a much clearer idea how the synthesis is working. Okay, so that's the last question. Very simple question. Okay. So when we run the synthesis on the right, okay, if we want to write the synthesis, is the synthesis able to run? If we run this, if not, what's wrong? Okay, no, yeah. Because it defines no synthesis, that means you will use this portion of the code. Yeah, this portion of code, memory allocate, is not supported in high-level synthesis. Okay. Oh, the question 2. Okay. Given this code, yeah, this code we already seen that. Okay. And assuming the following resource, A array and B array are in the same memory bank. Okay, they save in the same memory bank. And this memory bank is only single port memory. Only single port. And C array is in another memory bank. Yeah. And each multiplier available with 2T latency. That means the multiplier takes 2 cycles. Yeah. And we want to do the pipeline here. Can you tell me what the II can be. So definitely you need to draw the waveform like to draw the timeline. Try to figure out what is the II. It's hard just to think in your brain. You need to draw something to figure out. Okay, Dongxian answer 2T, right? Okay, yeah. So you can see, since there's a single pole and you have a low A and B, so you have a low A and then low B, and then you have a 2 multiplication, and then you have a stall. And when can you have a start next one? You definitely cannot start next one here, right? Because you will be low A, since A and B in the same array, and that array, the memory array only single pole, so you cannot have here. So you have to move here. So low A and this low B, and then you do the multiplication and do the multiplication and then stall. Yeah. So I equal 2 can meet all the resource requirement. Yeah. Okay. Good. Yeah. Okay. So I think today I could not finish the lab 3. Okay. There any more question for this one? That's the end. Yeah. Okay. Okay. Yilin, yeah, you have a question, right?
Okay, yes, I just
Please.
wonder that. So this II will be calculated by the compiler if we signify the pragma, then the compiler will calculate the II for us
Yeah,
automatically.
yeah, yes.
Okay.
Of course, you can still say I want to do II equal 1, and the compiler will say no way. Unless he will suggest use a 2-pole RAN.
Oh, all right. What if
But
yeah.
since you already specified that the memory is a single pole RAN to use.
Oh,
Yeah.
and what if we state so many pragma and some of them are they conflict? What would the compiler do?
Oh, you mean some of the pragma will conflict?
Like, yeah, for example, the pragma says the latency is under such latency and the area also under such area, but it's not gonna happen. Then what will compiler do?
Yes, but you don't specify area. The pragma doesn't have a control on the area. Yeah, so it's maybe another example, but I get your point. Yeah. Somehow the pragma self-conflicting each other, right?
Mm-hmm.
Yeah.
Yes.
And or simply because the resource limitation, you cannot achieve the target II that the user specified. Yeah. So in that case, the compiler will try the best to get you the best II. Yeah. And if you really don't satisfy with the compiler result, then you need to go into look at the timeline and to figure out what is the bottleneck, what is the limiting factor that prevent to achieving that II. And then you can either increase the resource or restructure your code. For example, dependency. The compiler say there's a certain data dependency. I simply could not do this operation at this cycle. I have to delay at one actual cycle to avoid the data dependency or conflict. Yeah. If that's the case, then you need to figure out how to, and then you have to investigate what compiler thinks the data dependence is real or not. Because compiler doesn't have a global knowledge. Because that signal coming from outside, and outside maybe you have a module to resolve the conflict, but the compiler simply have no view on that. It doesn't understand. And you as a designer know the whole design, and you know that dependency won't happen. Then you can use the pragma, say, dependency false. Tell compiler, say, that's not the true dependency. Go ahead to ignore this dependency. Yeah. Because the compiler will, since it is static, then it has to be very conservative because the circuit he generates must working, right? Must work. Yeah.
Yes.
Yeah. Then so that's where human knowledge comes in to assist the compiler using those pragma.
I see.
Okay.
Thanks.
Yeah. Okay. Any more questions? Yeah, I try to explain things clearly so that you all fully understand. I think it's very important for engineering work. You have to know every detail. Yeah, and that give you a capability that you can do debugging. Yeah, you know where the problem is, and then yeah, give you a direction where to embark on. Yeah, so that's why I'm speaking quite slow. Plus, I have a bad English. I could not speak fast English. That further slow down the course. Okay. So we will call today. So today I also lack one slide. Yeah. I will try to make a